Hi everybody, welcome back to today's session on multi-head attention. In the last video, we learned self-attention and applying mask on the self-attention. Today we are going to see, using that self-attention, how we are going to split them and use them multiple times, which is called the multi-head attention. We will learn how to implement that through our own code, as well as we will see how the library in TensorFlow have implemented the same concept of multi-head attention. Apart from that, we are also going to understand in depth what is the need for multi-head attention, what purpose it serves. Okay, so let's start. Very quick refresh on how we had built the self-attention, which was used only once, so therefore this could be thought of as a single head self-attention. So the words were coming as a embedding vector, and they were passing through the Q network, which is to convert them as query. It is a linear projection or a neural network without activation or a linear activation. So this is how the query will be transformed into a matrix. Then the keys will be also formed from the same words and the values will be formed from the same word. They will all go to the self-attention layer, which is a function of QKV. Internally, they are doing a dot product between Q and K transpose. Then they are scaling them by dividing its square root of the dimension of K, and then finally that result is getting applied. That this part gives you this particular QKT by square root of DK is the attention score, which is now applied on the V. That gives you the weighted output of the words, right? That gives you which word is creating what kind of impact. Now let's go to the multi-head attention. First thing we will be doing is that we know the D model, which is a parameter, hyperparameter, and let's consider for our purpose this example is that 512 is the D model, which is basically the output dimension at each layers. So transformer has many layers. What they ensure is that every layer has the same, the layer output has the same dimension of D model. Now the D model, if it is 512 for our case, which is the embedding output 512, first thing we have to decide, we take a number of heads. How many times the self-attention to be used is the head, right? So, let's consider that head is 8. One thing we have to ensure that D model is replaceable by the number. So we choose 8 such that your DK DV becomes 64. 64 into 8 is 512. If it is 8 number of times we will be doing the linear projection to form our Q. So the output of this linear projection is going to be 64. We have given 512 as the entire input data. 8 times we have done the projection. Each one of them's output is actually 64 number. So 64 dimension, which is DK. We have got a projected output of Q. Each one of them is 64 and 8 such number. Similarly, we do it for all the word, therefore this becomes a matrix, very similar to what we have done for self-attention. Then same thing is done for key and the values as well. So we have these 3 Q, K, V. Each one of them is now not a single matrix, but there are 8 number of matrices. All of them are now passed to the self-attention. All of them will be parallelly using the self-attention. So therefore the result from the self-attention is 8 number of attention weighted values, 8 number. But then they will be finally all concatenated. You see the plus signs here, that means they will be concatenated, all these 8. So we are back to 64 into 8. 64 and 8 times with them, sum them up, join them together, concatenation, finally pass them through another neural network, which is a linear projection. Once again, output is again going to be 512. We started with 512, got the output as 512. In between, we had projected 8 times, calculated their self-attention separately, then again joined them back and then created the TM. And then finally, you get the output of T number of steps, AT, attention, and then DM is the output. That's all about the concept of multi-head. The representation in the paper has been given in this manner, which is your Q 8 times projected, K 8 times projected, V again 8 times projected, multiple times projected, and use the scale dot product attention, concatenated, then linearly projected. Exactly same thing we have. The paper is building it on step by step. They first explained what is scale dot production, then reuse them 8 times for creating a multi-head attention. Our code is also following that. However, when we go to the libraries, we will see that it is actually mixed up there. So that's how we have taken the trouble to build block by block. Okay. Now, why this is done? To understand that, let's focus here. So let's consider that we have this sentence, which is, while Jenny read a book in the garden, her brother played the violin in the living room. Now there are several things going on in this one single sentence, right? So the first thing which is happening is a spatial relationship. One is there in the living room, another is in the garden. So one head will be able to understand how they're placed, the spatial relationship. There is also one thing happening here, which is while, which means this is happening. Whatever is happening, it is happening concurrently. So maybe another head will focus concurrence, and then the another head which could do the mapping, who is doing what. So basically one is reading and another is playing violin. So Jenny is associated with the reading, subject action mapping. The subject here is the book, reading, and who is doing that? The Jenny is doing. So Jenny is reading while her brother is playing violin. So that is how the action and subject and action mapping is happening by another head. Yet another head could be trying to gather, right, objects involved here. Book, violin, they are the object. And associated with whom? Book is associated with Jenny and the violin is associated with brother. You can see how many dimensions you need to capture from a single sentence, and if it is a single head, it will only serve one purpose. If it is multiple head, it is trying to capture all these nuances. Essentially we are talking about, unless there is a multi-head, the entire model would have focused attention only one aspect, right? So that's how I think this is a very important stage we need to capture in our mind, is that this is the building block of, let's say, today's ChatGPT. You give one sentence and you can see that it is playing a magic of giving you answer from all aspects. Whether what his brother is doing, it will answer immediately. Where his brother is, where Jenny is, so they will be able to give the spatial relation to how it is able to do. You will recall in one of our previous video, Dawn of Self-Attention, we said that there are different types of tasks. One task using which we are building up our attention mechanism is the encoder, decoder, the translation. But translation is not the only task. There are tasks like NLI, natural language inference. There are tasks like classification, word sense disambiguation. On all those is basically understanding the word itself or the sentence itself and how one word relates to another word. And that was the foundation some time back, long time back, before transformer. Now when you are coming to transformer, we are saying that is further getting extended, getting the last bit of information from the sentence is the aim here. It's not only self-attention, it's not only one word how it relates, but one word relates to other from different angle. Therefore, you are building general purpose model, which is not serving one task. It is meant for multitask. It is able to generalize, understand the language for many other tasks. And that's how the capability is coming of, let's say, the artificial general intelligence, a very baby step towards that, and that's what your ChatGPT today is demonstrating. One problem was that we had very limited capability, which is the sequence length. Transformer removed it. We displayed it in our previous video by the table, which very clearly explains where your computational complexity, path length is getting improved. So therefore the length of the sequence is addressed to a very large extent. Now this is another mechanism, multi-head. It gives you detailed understanding of the languages. Fair enough. So now let's go to the code. Our own implementation of multi-head attention. Here we are inheriting layer as before. Then you are giving number of heads as the input when you are instantiating this class and the D model. Then we are making sure this assert statement that the D model is actually divisible by the number of fades. So we take 512, then this should be 8, so that your final depth, which is this output dk or dv, has to be 64. Then we have this dense layer as before. You are utilizing the self-attention which we have built before. This is where we are initializing the self-attention layer, right? And then we move on. All this we had explained, what each of them use mask and row mask, all those are done. We are going to the split head. This method takes the input, x takes one input, then split them by their number of heads. So here is the input data, and then the output shape will be batch size, the number of fades, then sequence length, and the remaining, whatever is the value remaining, that it will do. Which means if you have given 512, then that 512 will be divided between number of fades and the 64. So 8 into 64, whereas sequence length and batch size will remain as is. That's what we are saying. Now you are going to the call, where the first thing which do is extract the mask information from the raw query key and values. The split operation, which where inside you can see the x is not raw, but x is actually passed through the dense layer, right? And so we are doing concurrently. We are doing a linear projection. At the same time, we are doing it 8 times, correct? So by this projection as well as the split head, 2 operations are happening parallelly. One is the projection, another is also ripping them or the splitting them into 8 heads. As a result, the mask information will be lost. So therefore we captured it here and then again giving it back to them. This is done for query, key and value, same thing has been done. And then we are pushing the mask information which we have captured here back to the QKV once again, because QKV is no more the raw data where mask was there, but QKV were the projected data passed through a neural network and reshaped. So the mask information was lost. We have given it here. One thing you need to understand, that this mask is only going once. Although QKV is now will be passed to the self-attention 8 times, there are 8 number of this thing going, mask information is 1. So in one place within self-attention, if you remember, we had repeated this. There was a repeat line. You can go back and check it once. So that's how, since this mask is only going 1, but we had 8 number of such QKV which is going inside. Therefore, the mask has to be repeated. Fair enough. So you see, before the data goes to self-attention, we have to remove the head. We have done this job here. See, once the split head operation has happened, we have the batch head, number of head, sequence length and depth. That's how the information was split. But our self-attention don't understand what is the head. So therefore, what they will do is they are expecting the QKV, they expect the information to come in this manner, which is batch size, sequence length and depth. That's how your self-attention will expect. Therefore, what we are doing, we are multiplying the batch size and number of it and passing it as if this is a batch. Self-attention will do the attention calculation based on this entire lot. After you receive the attention output from the self-attention, you will again reshape them. You will again reshape them at this line, reshaped, to make it batch size, number of fade, sequence length and the depth. This is a little bit reshaping we are doing to make it compatible with the previously built self-attention layer. Fair enough? Now you are doing the concatenation, which is basically this number of heads and this depth, which is 8 number of 64 attention output. We are going to concatenate. So it again becomes 512. And then finally pass them through a dense layer. And that's what we get the attention output here. That's all about our implementation of the multi-head. Let's go and test it quickly. Here we are doing the initialization. As you can see, multi-head initialization we have done by giving number of heads, which is 8. D model was already 512. Then this is passed through all QKV, same data. Embedding data is coming from the positional encoding. I'm not going there just to cut short time. So embedding data is coming from the positional encoding, right? We have here positional encoding. That output was P class. You remember this is the embedding data, which is fine. Fair. Let's go there. Now what it gives you, notice it here that this is a check to confirm our things are working properly. Q before splitting is 1, which is the batch size here. We have taken only one instance. Ideally it will be 64 or whatever. And then this is the sequence length 101. This is our depth or the embedding dimension. Once the split operation is happening, we can see it is working perfectly. The batch 8 number 512 is split into 8 into 64. Sequence remains same. Okay. Same thing is done for QKV. And then before it is going to self attention, we are multiplying this 8 by 1. 8 into 1. So if it is 64 into 8, it would be that many numbers combined together. Gone to self attention. This is the KV, which is also prepared that way. Therefore, we receive the score. Score is 8 number of square matrix. That is how this square is now applied. We are not spending time here. These are all explained in the previous video. Masking, how the masking is working. Then finally, you come here and you see that the, hold on. So basically here you are getting the attention output, which is 8 number of 101 sequence 64. So this we have to again concat, which is 8 number of 64 will be concatenated to give you this 512. Right? This will be 512, and this 8 is within this 8, it is 8 into the batch number. That was the thing. So batch number has been separated as 1. If it was 8 into, let's say the batch was 2 instances, then it will be 16. Then here you will see this is 2, and still it will be 8 into 64, 512. That's how this operation is happening here. Yeah, that's it. I think another thing, I think this is talking about the mask, that the columns are made 0. The rows, we have a parameter here to turn them as 0 as well. We explained during, but here last video, here we have not done so. And like we were explaining last time, that the default implementation, although mask was applied, because this row, all the values in the row are equal, the softmax will give us equal weight to all of these values. That's what is happening. And then I said that we have a implementation where we found it more logical to set them as 0. Fair enough now. So this is about our own implementation of the multi-head attention. Fine. Block by block, what is happening you can see. Now let's see how the original Keras layer have implemented it. Let's go there. You are able to view that this is what is the original Keras layer. You see that this is under Keras layers attention, and then multi-head attention.py is the file where you have the implementation. Now if you go to PyTorch don't have the implementation done in Python. So you will be able to locate, there is a nn.multi-head attention which is there. But if you open that code, you will see it is calling a lower level module, which is written in C or C++, which is doing the multi-head operation. By using Python, we can't understand how they have implemented. You have to go one level down and then understand how it is written in C, right? That's a separate exercise, maybe we'll do one day. Now today, see how Keras has implemented here. If you straight away go to the Keras multi-head attention and go where they are computing the attention, compute attention, we see some similarities. For example, query is scaled here, multiplied by the square root, right? Then attention score is getting calculated here. How we were doing the calculation? We remember we are doing a tf.matml between q and kt, right? What they are doing? They are doing a EIN sum of some equation and then key and query. Almost similar, but what is the EIN sum? Is the Einstein summation. Einstein summation was the concept wherein when you are dealing with a large tensor, instead of doing a matrix multiplication or a, let's say, a linear projection or a transpose, I mean, all these different types of linear algebra can be generalized by giving some kind of notation. For example, in the matrix multiplication, last dimension and the first dimension of the two tensor cancels out, right? So these are some of the pattern. If we are implementing it, then we can generalize many linear algebra operation. We have to understand the Einstein sum here. So here one, they have implemented this one, then they are applying the masked softmax, which more or less we have copied, and our implementation is almost same. So therefore nothing, we will skip there. Then we can see that they are applying this weight again, once again on the b, right, the value. So twice we had done the matrix multiplication, they are doing the same thing twice, the Einstein sum. Their q's are expected to be the linearly projected q. Within our implementation itself, we had done the projection here. They are doing the projection beforehand, and even during the projection, so basically they are generalizing, they are also doing it through Einstein sum, but rather only the equation changes. For example, if you come here, you see they are building two equations. One is for the projection equation, another is for the attention equation. Now let's see what is this Einstein equation all about. So to understand the Einstein equation, we take a small example here. This is our Q, randomly initialized 28512, where 2 is our batch number, 8 is the sequence length, and 512 is the embedding dimension, right? And you consider this as A, B, C. Now this is the W matrix, which is the weight, the neural network, right? Where what is this 512 are the embedding dimension. So this 512, 512 normally get cancelled out in a matrix multiplication. This 8 is the number of aid, and 64 is the output dimension that we say. So that's what we have written: embedding dimension, number of aid, and key dimension. Now we want to do the matrix multiplication here, but we want to do it through EIN sum. In EIN sum, we consider this as an equation like this: A, B, C. This is A, this is B, and this is C. And here we have the C common, then D and E. So A, B, C and C, D, E are two tensors. Output, we know that the C cancels out, gives you A, B, D, E. You understand the beauty here, right? So therefore, if you had somehow create the equation, then apply it on EIN sum will give you the same result. And this equation could be different for a matrix multiplication or a addition or some other operation, linear algebra operation. But if we are able to give the equation to EIN sum, one operation would be able to give you all the output. How do you build this equation is the question now. Let's see here. Free dimension. Let's understand build project equation. There is something called a free dimension. What is free dimension? Free dimension are those which are not going to change during the operation. For example, the batch, which is A in our case, and the sequence length, during the matrix multiplication, we are not going to change them. They remain same. We don't disturb them. So the batch and the sequence length are the free dimension. How many free dimension we have? 2. Right? One is the batch, another is the sequence length. So free dimension is letter 2, which means from this letter, all A to Z, we take A and P. These are our free letters. Remember that. Then the bound letters. What is bound letter? Bound letter are those where we will actually do the operation, which is the embedding dimension. In this case, it is only 1. So therefore, we are saying you start from 2 free dimension and then go up to 2 plus 1, 3, which is nothing but C. So A, B, C we have taken. Output letters. So this is the bound letters, which is A, B, this is the C, and then output letters is the, letters starting from 2 plus 1, which is you start from 3 and then go up to 5, which is 2 plus 1, 3 plus output dimension. As we know, output we are expecting as number of 8 and the output dimension, which is 64. So 8 and 64 are the two things which we are expecting. So therefore output dimension is starting from 3 are going up to 5. So that's what exactly we have done. We have gone up to 3, A, B, C, D, E is the output letter, right? So now we are forming the input string. Input string, we are going there, we are saying that this is free letter and bound letter, which means your input string will be A, B, and the bound letter we know C, so A, B, C. Output string is the bound letter, which is C, and then output letters, which is D, E, right? This to D, E. So C, D, E are the wait string, and the output string is going to be free letters, which is A, B, and the output letters, which is D, E. So C is not there. As a result, when you do this operation, we are seeing that if you do the build project equation, we are given all this, which is pre-dimension is 2, bound dimension is 1, output dimension is 2, you automatically get A, B, C, one tensor, C, D, E, second tensor. In between C cancels out, we get A, B, D, E as the output. You got the beauty of this Einstein operation. So this is for projection. Similarly, the scale dot product will have this dot product notation. The equation out here is like this, that we want this to happen, where what cancels out? The D, the last dimension, cancels out. We want to maintain the Q, PQ, BHQ, and the BHK. So we want BHQ and K, but the D cancels out. So if you are able to build this equation using a similar formula which you have developed, and then we are done. The actual formula which they have done, if you see even the projection, what we had learned in depth, the code will be building this. We have done a slicing here. What is free dimension, right? What they are doing is little different. They are also doing slicing, but they are doing it in a loop for I in range. So they are trying to build each one of them. They are just trying to build A and B. We have done the one slicing. They are doing one by one. A, then add B on top of that in a iterative loop. So that's how their implementation differs. But I found it easy to understand in this manner. So this is how the Einstein equation works. And they argue, I think, if you just look at this, the both implementation at the end, we'll see this will perform little better in terms of your accuracy, or the training time will also improve when you go by this one. Okay, that's it in this session. In the next session, we are going to now utilize this multi-head attention, the positional encoding, and build the encoder layer altogether, the encoder layer. And then with this encoder layer, several times is to be used. There are 6 number of layers as per the paper, which will be used to stack the encoder layers, which will act as a transformer encoder. Then subsequently we'll build on that before we do the enter step. See you then in the next video.